The topic of our today's lecture is voice transmission in subscribers loop. We are primarily looking at the voice transmission over our subscriber loop, which is primarily a copper wire pair based. Basically, we have already discussed what type of links do we have from our subscribers end or the subscribers telephone set to the telephone exchange. Uh, Basically, it is a combination of two wire lines, two wire sections from the telephone set to the telephone exchange. But we now need to see what are the impairments that we can face while transmitting our voice over baseband from our telephone set to the telephone exchange. At the telephone set, uh, the our acoustic signal, our sound signal, it is converted into the electric signal by the mic, um, and it sends it over this subscribers loop up to uh, the telephone exchange. Up to the telephone exchange, we have already studied that uh, we follow a two-wire system. It means that on these two wires or one single pair, both the transmission and reception are taking place. But when our voice is to be sent from the exchange to another exchange or somewhere else, it has to be converted into a four-wire system. Secondly, once when we have to manage our voice from the telephone exchange, apart from the conversion from this analog signal to digital signal, the other thing that is done is that it is converted from the two-wire system to the four-wire system. Now the basic building block for transmission is the telephone channel or the voice channel. Primarily, we have a human voice consists of a bandwidth of 0 to 20 kilohertz. But when it is to be sent over a telecom network, it means that it has to be converted into an electrical signal. Then it is observed and it has been experienced that uh, we do not require to send the complete 0 to 20 kilohertz band for a single voice. Even we can send the earlier 0 to 4000 hertz for that purpose. Not even that, if we send um, 200 to 3200 hertz of a band of a person's voice, it is easily intelligible at the other end, because this much band contains a lot of information about the speaker. Not only at the other end we can recognize the speech, we can recognize the speaker also. All the telecom systems are basically based on 0 to 4000 hertz band, and and all the digitalization of this voice channel is done while considering a voice channel from 0 to 4000 hertz only. We do not need to go to send the remaining 4000 to 20,000 part. So if we have 200 to 3200 hertz band, it is an optimum trade-off between economics and the quality of voice transmission. By economics, we mean that uh, uh, only this much bandwidth is required for a single voice. If we have 20,000 hertz, then the available bandwidth that we would have in our telecom systems would not be enough to cater as many customers. On the other hand, the quality of this voice, which ranges from 200 to 3200 hertz band, it is quite good and it is intelligible at the other end, while we can identify the speaker also, as you often observe in your telephonic conversation. Now we'll see what are the basic impairments of the voice channel. Primarily, the basic impairment is attenuation distortion. Then we have phase distortion, and we have noise distortion. After that, we have two separate categories of impairments of a voice channel, and they are called echo and singing, because echo and singing are primarily annoying factors at the other end. If on the other hand, or even at your own end, if you hear your voices echo, you will not feel comfortable. So it is better to get rid of all of these, or reduce all of these impairments as much as possible. Now let's see, first of all, what is distortion? What is the definition of distortion? Distortion means that the signal, received signal, is not the exact replica of the sent signal. It means that at the receiving end, the received signal is not like the signal that was sent at the transmitting end. There are some changes. The changes, why do we have those changes? Uh, we have those changes because of uh, amplitude, or the um, attenuation distortion. Attenuation distortion, or the phase distortion, or the noise. Now let's see what is attenuation distortion. It is the result of imperfect amplitude frequency response of the voice channel. It means that we have a range of frequencies that we generate at our end before transmitting it into the telecom system. We have a range from 200 to 3200 hertz, for example. If the transmission media does not have the same uh, effect on all the frequencies as per the attenuation is concerned, then we will have attenuation distortion. It means that if we have uh, more attenuation for the higher frequencies and lesser attenuation for the lower frequencies, it would cause an attenuation distortion. Similarly, uh, uh, for loaded pairs, higher frequencies are attenuated more in lower frequencies, and there is a very valid reason for that. For in the loaded pairs, we have um, inductors in our loop, which cause the attenuation of the high frequencies more as compared to the lower frequencies. Uh, Now, one more thing. Uh, how can we avoid it? The attenuation distortion can be avoided if the frequencies in the passband are subjected to the same gain or attenuation. Means that all the frequencies have same attenuation. On the carrier equipment, attenuation on the band limits is higher and it is lower in the middle. Now, how can we measure attenuation distortion? Uh, there is a European requirement of measurement of attenuation distortion, and there is a system of attenuation distortion measurement in US. In the European system, uh, between the frequencies 600 Hertz to 2800 Hertz, the level will vary only for not more than -1 to +2 dBs. Now, here the plus sign means more loss and minus sign means less loss. So if a signal at -10 dBm is placed at the input of the channel, we would expect -10 dBm at the output. If But that would occur only if there is no attenuation at all. But what happens, and we are measuring it at 800 Hertz. But at other frequencies, we would expect a variation between -1 to +2 dBs. Now, I would like you to understand that the initial signal that is being sent, its units are -10 dBm, and the gain or the loss in between, that is given in dBs, and that ranges between -1 to 2 dBs. And this is, we are not talking about the same 800 Hertz at which the -10 dBm that we were expecting, this -10 dBm at the other end. We are measuring the attenuation at other frequencies. For example, we might measure a level of attenuation at at 2500 Hertz to be minus 11.9 dBm, and at 1100 Hertz we might find it at 9 dBms, which means that at 1100 Hertz the attenuation distortion was -1, while at 2500 Hertz it was +2 or plus 1.1, 1.9. So what would happen, that it would go from minus 11.9 dBm at 25 Hertz, 100 Hertz, and at 1100 Hertz it would be 9 dBms. This diagram shows this particular case that we just described. We have got attenuation in dBs, and which is relative to the attenuation at 1000 Hertz, and we have got frequency given on the x-axis, while going from 300 Hertz to 3400 Hertz, which is the quite active region for the human voice. You can see that the attenuation varies from between -1 to 2 all the way, but from 1000 to 3400 it varies between -1, rather -1.5 to approximately 1.5. At between 300 to 1000 it varies between -1 to 2, and the actual signal attenuation, it varies given as given by the curve or the line. that varies in between, and you can see its variation as compared to the zero line or the datum line. Now, what is phase distortion? A voice channel is basically like a band pass filter. It allows to pass a few frequencies and some higher frequencies and some lower frequencies, and not beyond that. Uh, the finite time a signal takes to pass through a network is a function of the velocity of propagation. It depends upon which frequency are we sending. It means that the velocity of propagation of the sound is different at different frequencies. And how does that happen? It happens because of the electrical characteristics of the media in between, or of the voice channel in between. Velocity of propagation is higher towards the band center and less towards the band edges. It means that the frequencies which come exactly in the center of the whole band from 200 to 3200 hertz would uh, would the velocity of propagation of those frequencies would be quite higher as compared to those at the highest level, or which is nearing 3200 hertz, and the lowest level which is nearing 200 hertz, and their speeds or the velocity of propagation and on the extremes is lower. So there would definitely be a relative delay along the voice channel, because the mid mid frequencies would reach the other end earlier, while the uh, extreme or the least frequencies and the highest frequencies would reach the other end, the receiver, later. The finite time it takes a signal to pass through the total extension of a voice channel or any network is called delay. Absolute delay is the delay a signal experiences while passing through the channel end to end at the reference frequency. And that reference frequency can be taken as 800 Hz in case of European standards and 1000 Hz in case of American standards. The propagation time is different for different frequencies, with the wavefront of one frequency arriving before the wavefront of the other frequencies, other frequencies in the passband. If the phase shift is nonlinear with respect to the frequency, the output signal is distorted compared to the input. And how do we measure it? What are the parameters? We call this parameter EDD, or the envelope delay distortion, which is the derivative of the phase shift with respect to frequency. The maximum difference in the derivative over any frequency interval is called the envelope delay distortion. So, envelope delay distortion is always a difference between the envelope delay at one frequency and at another frequency of interest in the passband. So, envelope delay is often defined as the group delay. Now, group delay, which means that the ratio of change with angular frequency of the phase shift between 2 points in the network. You can see in this diagram that that shows how the differential delay varies and we can see a range between 1700 to 1800 where it is the minimum and the flattest also. That is why if we want to send some signal in the digital format, we use these two frequencies, 1700 and 1800 hertz. Now the absolute delay is minimum around 1700 and 1800 hertz. The figure also shows that around 1700 or 1800 hertz, the envelope delay distortion is flattest, and that is why uh, the data modems use 1700 or 1800 hertz for characteristic tone frequency, which is modulated by the data. Phase distortion or EDD has little effect on speech communication, so it is more of an effect. It has more effect on the digital communication rather than the analog communication or the voice communication. The third factor of impairment is basically the noise. There are multiple types of noise, like thermal noise, intermodulation noise, crosstalk, impulse noise. Now, what is noise? Noise consists of an undesirable signal in a communication circuit. Now, first of all, let's see what is thermal noise. Thermal noise is the general expression referring to the noise based on thermal agitation. Basically, it is also called the white noise, and it refers to the average uniform spectral distribution of noise energy with respect to frequency. It is directly proportional, the thermal noise is directly proportional to the bandwidth and temperature. If the bandwidth is 1 Hz, then the thermal noise would be K into T, where W uh, is and it is given in watts per Hertz. So where K is the Boltzmann's constant, 1.3 into 10 to the power minus 38. Uh, 1 into 10 is 1.38 into 10 to the power minus 23 joules per Kelvin. Now, what is the reason or what is the physical reason behind the thermal noise? The main reason behind the thermal noise is the electronics of the transmitter and the receiver. Uh, if we have 17 degrees centigrade temperature, if we convert it to the Kelvin scale, it becomes 17 plus 273, which gives us 290 degrees Kelvin. And the Boltzmann's constant is, as you know, 1.38 into 10 to the power minus 23 joules per Kelvin. Then the thermal noise power would be 4 into 10 to the power minus 21 watts per hertz. If we have a value of the bandwidth over which the signal is being sent, then we can multiply the bandwidth also, and we will get our thermal noise in terms of watts. For a band limited system, that is the system with specific bandwidth, Pn is equal to Kt into B, and this would be given in terms of watts, where B refers to the so-called band, so-called noise bandwidth in hertz. Thus, at 0 degrees Kelvin, we obtain Pn is equal to minus 228.6 dBW per hertz of bandwidth for a system with a noise bandwidth measured in hertz, which is B, and Kelvins degrees Kelvin temperature. And if we convert the formula uh, KTB, which gives us the result in watts, to dBs, then we get uh, uh, the the form of this the the following form of this formula. It would be Tn is equal to minus 228.6 dBW plus 10 log of T plus 10 log of B. Now let's see what is the second type of noise. The second type of noise is the intermodulation noise. Intermodulation noise is the result of the presence of intermodulation products. If two signals with frequencies f1 and f2 are passed through a non-linear device or medium, the result will contain intermodulation products. How do we get those uh, intermodulation products? If we have two frequencies f1 and f2 passing through our device, and our device is exhibiting a non-linear response, it would result in the production of second order, third order, and fourth order products of these frequencies. First order products are themselves F1 and F2 separately. Second order products would be F1 plus F2 or F1 minus F2. Third order would be 2F1 plus minus F2 and 2F2 plus minus F1. Fourth order would be uh, 2F1 plus minus 2F2 or 3F1 plus minus 3 plus minus F2. It means that the addition of the frequencies and the addition of multiples of these frequencies would result in the production of a large number of intermodulation products, which would cause somewhat like uh, uh, thermal noise or white noise, but actually it is not white noise. Why do we have intermodulation? Due to um, uh, due to nonlinear uh, uh, performance of electronics, of the transmitter, of the receiver. For example, if we have, first of all, if we have improper level setting, if the level of input to a device is too high, the device is driven into its nonlinear operating region. Means that it is in the overdrive region. In this situation, uh, the device would be in a non-linear operating region, and it would definitely produce multiples, additives, and multiples of the frequencies that are working in this electronics. Secondly, improper alignment causing a device to function non-linearly. Thirdly, nonlinear envelope delay would also cause intermodulation noise. And fourthly, the device malfunction would drive it into, can drive it into a nonlinear region where the production of intermodulation noise because of intermodulation uh, products is imminent. The third impairment in our telecommunication systems regarding voice is the crosstalk. Crosstalk is basically the unwanted coupling between signal paths. There are three causes of crosstalk: electrical coupling between transmission media, poor control of frequency response of the effective filters, or the non-linear performance of the frequency division multiplex systems. The excessive level will increase Crosstalk. There are two types of crosstalk. Intelligible, which means four words are intelligible to the listener. Uh, four words are intelligible to the listener from extraneous conversations in 7 seconds period. And the other kind is the unintelligible, in, which is defined as the crosstalk resulting from any other form of disturbing effects of one channel on another. The fourth type of noise is the impulse noise. Impulse noise is normally non-continuous, irregular pulses of short duration. They might have broad spectral density also, but they have high amplitude. They have less effect on voice telephony. It means that they have less effect on analog communication, but it seriously degrades data error performance in case of digital communication. And now we need to see what is the level of a signal, of a voice signal. Voice signal, when it is digitized or when it is converted into an electrical signal, uh, it is measured in terms of its level or the signal magnitude. And the level has the primary importance in analog communication. But in digital communication, it is of secondary importance. In communication networks, the level is measured in terms of dBm, where dBm is the dB's reference to 1 milliwatts. In the radio side, it is measured in dBW, which means that the dB's reference to 12 watts. In TV or the video, it is measured in terms of dBmV or the dB's reference to 1 millivolt. Now let's see what is zero test level tone or the zero test level point. It is the point at which the test level tone is 0 dB. Then we have got a term dBr, which is the decibels reference. If we want to calculate the value or the exact value dB in dBms, we need to have a dBmo plus dBr. For example, if we have minus 32 dBms of a signal at minus 32 dBr point, it corresponds to the reference level of minus 10 dBm. It means that minus 10 dBmo. A minus 10 dBmo signal introduced at 0 dBr has an absolute signal value of minus 10 dBm. So we get the value of signal in terms of dBm when we have it uh, in as an absolute value. The absolute value is given uh, in dBms, and the reference value is given as dBr. dBmo is basically the is the zero test level point. Now, what is signal to noise ratio? It expresses in decibels uh, the amount a signal exceeds the noise within a specified bandwidth. The required signal to noise ratio values of voice are based on the customer satisfaction. For example, the voice may be of 40 dBs or 45 dBs. And in case of if it is 40 dBs or 45 dBs, then it would be an intelligible voice for humans. But if we are sending some data, then 15 dBs would suffice. And but that is also specified based on the error rate and the modulation type. Uh, in normal telephony, signal to noise ratio uh, has very less applicability because the signal can fluctuate, because when we talk, um, our our speech has different points of stress. So there are different levels of signal during human speech. So signal to noise ratio is uh, um, is not the right way of assessing how good a speech is reaching the other point. So signal to noise ratio is considered when we are using data communication. Here in this diagram, you can see that we have got a signal level at 15 dBms, and the noise floor stays at 5 dBms. In this case, the signal to noise ratio would be 15 minus 5, and it would be 10 dBs. So the signal to noise ratio is the level given in dBms, signal level given in dBms minus minus the noise level in dBms. When we subtract the noise level in dBms from the signal level in dBms, we get the value of signal to noise ratio in terms of dBs. Now we need to convert our two-wire system, which is given uh, in our telephony network. For example, as we have already discussed that we have got two wires for two-way communication between a telephone set and the telephone exchange. But we need a four-wire transmission when we are using carrier or radio systems. Carrier means the communication of a voice channel between a telephone exchange and another telephone exchange. Radio systems mean when we are trying to send a, a multiplex signal over a radio transmission system. In that case also, we need to convert those two wires uh, signal, which have both the incoming and outgoing, or the received and the sent signals of voice. Uh, Here in this case, the received and the sent signals are kept on two separate uh, pairs. So we have got a four-wire transmission system. In this example, figure sorry 5.4, a typical long distance or toll telephone connection is shown. There are terminal sets on both the sides. Terminal sets are basically hybrid transformers, which has four pairs of outlets each. On the right side, you can see actually the right side and the left side both are basically the same. But on the let's consider the right side. What happens is that two-wire uh, telephony signals are coming from the right hand, and they are entering the terminal set. The terminals from the terminal set, they are converted into four wires, which go above the terminal set and below the terminal set. Two go above the terminal set, two wires go above the terminal set, and two wires go below the terminal set in this diagram. And both of them are for reception and transmission separately. While we have got another block N, which is connected with a pair of wires to the terminal set. What is this N? N is the balancing network. What is a balancing network? Network uh, that is based on an RC circuit, a tunable RC circuit. Why do we need this tunable RC circuit? This tunable RC circuit lets us balance the two sides, the input side and the output side of this terminal set. So in this way, uh, we have got we converted our two-wire signal from the telephone to four wires to be sent on the longer distances. Now, it is also clear in this diagram that we have got three uh, amplifiers on the lower side which go towards uh, the farther end, and three uh, amplifiers on the upper side which go towards the terminal set, to this terminal set. And our on the farther end we have got the terminal set uh, of our destination. Here also the two-wire uh, connection is coming into the terminal set, and it is converted into four wires above the terminal set, and the two wires above the terminal set and two wires below the terminal set. And again we've got a balancing network shown as the block N, which is connected using one single pair. Now how does that work? A hybrid is a transformer that works as a power splitter for the four sets of wire pair connections. Two of the wire pair connections relate to four wire path, which consists of transmit pair and the receive pair, as we have also already told. So we can move forward. We've talked about it. Here it is given in a more elaborate form. We have got a hybrid transformer in the middle, and two wire connection or the L side is coming in, and it is being converted into two uh, paths, one incoming path and one outgoing path, and it is being balanced by a balancing network N, which consists uh, uh, of an RC network, resistive capacitive network. But we do have some losses in the hybrid. Why did we uh, uh, take up this hybrid transformer in first place? Because we wanted to place some amplifiers on the transmit side as well as on the receive side. But there is a negative side to it also. And first of all, the hybrid insertion loss of about uh, zero point 0.5 dBs, and hybrid dissipation loss, which is approximately 3 dBs, which is half of the power is lost as hybrid dissipation, and zero point 0.5 dBs is lost as hybrid insertion loss. So there's a total of 3.5 dBs of loss when we use a hybrid or the terminal set. But the advantage is that we have got a four-way system, and we can place amplifiers on the reception as well as uh, transmission of the signal. Now we need to check how good is our terminal set or the hybrid transformer. It is given by the return ratio, and the return ratio is given as 20 log to the base 10 of ZL plus Zn over ZL minus Zn. ZL is the impedance of the two wire lines, and Zn is the impedance of the balancing net.